అది దాక్షలు కూడా ఎంతసేపు పెట్టుకున్నాడు బయట. తర్వాతనే వస్తుంది. అదే
పనికిరాని ఫోటోలు తీసుకుంటే వీటి దగ్గర తీసుకుంటున్నా అవునా. ఆన్లైన్ క్లాస్ ఆన్లైన్ క్లాస్ చదువుతున్నా. vibration energy levels of diatomic molecule. So how to calculate the vibrational energy of a diatomic molecule? So first we'll see the harmonic oscillator. So as a first approximation, a diatomic molecule, you know that diatomic molecules which are having the two atoms here, right? For example, here, okay. So this is the central. Okay. So here is atom one and two diatomic molecule here. For this diatomic molecule, here a harmonic oscillator generally it obeys the Huckel rule. So what is mean by Huckel rule? So Huckel rule generally Huckel rule, Hooke's rule, sorry. So Hooke's rule, so it states that the restoring force is directly proportional to the extent of stretch, right? So when you stretch a particular compound, right? For example, here, right? So this is the some mass, which is mass, right? It is when it is attached to some spring, right? So when you stretch this spring here, so it have the some right spring action, right? And on restoring, right? So it will be comes on the same position, right? So it is a restoring force. So Hooke's rule explains this thing only. So as per the Hooke's rule, which state that the restoring force is directly proportional to the extent of stretch. Now let us consider a spring, one end of which is fixed with a wall and other end is with a ball. So the ball is now displaced to an extent of delta x, right? So here the delta x is okay. So where the one ball is, right? One side it is attached with the wall here. Here is a wall, okay, and this is the ball here. And on this side, right, so it is attached to some spring, right? So uh, the ball is now displaced to an extent of delta x along with the direction, right? Reference direction. So such that the spring, which is assumed to be preferentially perfectly elastic, stretched to a some extent. The restoring force acting on this ball is proportional to the extent of stretch. So here the restoring force F equal to right, K is a constant here delta x. Delta x is nothing but it is a the distance, right? Right. So the distance, right? So extent, the displacement of the extent here. Here we have shown with the minus here, right? So minus K. So generally minus negative charge is it is indicating the direction opposite to that of the displacement of delta x. Okay, so here the K is a force constant here, and K is the force constant, which is the characteristic of the spring, and it is independent on nature of ball here, right? So it is not depends on the nature of ball. It is independent to the nature of ball. So now you can see uh, here. Let us consider the right the two balls attached to a particular spring, and it is having the two balls here, right? Here is a M1 mass, and here is a ball 2 M2 mass here. So here the x1 and x2 with the displacement of two balls. As the displacement is vector, you know that, right? So here the vector and the scalar. Vector means which are having the direction here, right? The magnitude and the direction. It have the magnitude and the direction here. Okay. And scalar, right? So it don't have the direction and magnitude here, right? So here the displacement, it is a vector property. It have the magnitude and the direction, and the extension of the spring delta x equal to x2 minus x1. This is the distance traveled by the two masses here. Now the Hooke's rule is applied where the restoring force acting on ball 1, right? Here in this case, we are taking the two balls with ball 1 with the mass m1 here and the ball 2 with the mass m2. Okay, so here the restoring force F1 equal to K x2 minus x1, where it is taken as equation 1, and the restoring force acting on the ball 2, it is K F2 here, K x2 minus x1, same, right? So same restoring force is applied. According to Newton's second law, where the restoring force acting on ball 1 is m1, m1 is the mass of the, right, the mass of the ball 1 here. Uh, right here the d square x1 by dt square. And similarly with the ball 2, restoring force acting on the ball 2 here is m2, where the m2 is the mass of your second ball. Now upon combination of the two equations, so we'll get the uh, right here the m1 d square by x1 by dt square k x2 minus x1. But the m2 also we get same thing here. And by this following this mathematical equations, so finally we get this the equation for the reduced mass is m1 m2 by m1 plus m2 here, where the mu, right, here the mu is the reduced mass here, right? So we get this equation to calculate the reduced mass. Now the selection rules for the harmonic oscillator. So where the selection rule explains the transitions allowed between the energy levels here. Okay, here we will see with the transitions here the V naught, right, vibration here. V naught here the V1 level, V naught level, V2 and V3. So these are the energy levels, vibration energy levels here, right? So here V naught to V1 transitions, sorry, vibrations are allowed. So here the transition, the vibration here, V naught to V1 is the most intense transition as at room temperature. The population of V naught level is very high when compared to other energy levels here. So this is because energy difference between the V naught and V1 level is very high when compared to the room temperature energy. And in the IR spectra, the very important the terminologies involved, right? The transitions involved is the fundamental bands, overtone bands, and hard bands, right? So this is very, very important terminologies here. So fundamental bands. So what are the fundamental bands here? How you get these fundamental bands? Here, the fundamental bands, nothing but where the transition, okay, right? So the transition allowed from V naught to the Vx here, right? Then it appears as a band, that is signal here. So here the with V naught, right? The V naught to the V transition V, it is allowed, right? So here the fundamental V1, V naught to V1, V1 to V2, V2 to V3. So these are the fundamental bands here, right? And then the overtone bands here. Overtone bands. So what are the overtone bands? So overtone bands, nothing but where, right? So in the energy level, right? So here is a V naught, V1, V2 here. So the transition allowed from V naught to V2, right? Or V1 to V3 here, V3. Okay, so leaving that, right? So V1, V naught to V3. So this is overtone bands, right? So leaving the V1, okay, V naught to the higher transition levels. Here you can see the transition. Here the first overtone where V naught to V2 here, where leaving the V1. Okay, so the trans won't observe the transition from V naught to V1 here. So it is overcoming that the leaving the V1. The transition is takes place V naught to V2 here. And second overtone is V naught to V3, right? V naught to V3, right? So this one, this is second overtone. And for example, if you take the third overtone where the V naught to V4 here. So like that. So starting from the V naught, right? And it is uh, starting from the V naught and it is leaving the in between trans energy levels is going to higher energy levels. So this is the overtone bands here. And hot bands. So generally the hot bands takes place at higher temperatures. Next, the types of molecular vibrations. So types of molecular vibrations. So generally here, the molecular vibrations, molecules are, right, they are having the vibrations, right? So like vibration means here, where, so they're doing the vibration because here the total energy, right? Here the total energy is equal to the E of electronic energy, E of rotational energy, E of vibrational energy, right? So where the molecule is having the electronic energy, the rotational energy, and vibrational energy, right? So the all energies are equal to the internal energy, right? The internal energy, total energy. So molecules are having its own vibration, right? So this vibration, due to this vibrational energy, the molecule is undergoing some, uh, right? The vibrations, stretching vibrations and bending vibrations here. So this stretching vibrations, it may be two types like symmetrical stretching and unsymmetrical stretching. So what are the symmetrical stretching generally? So here symmetrical means symmetry where the equal, right? So for example, we have this, right? So this is a central carbon atom and here is a H1, H2, for example here, right? So here is, for example, here the X, right? Here is the atom A and B, for example, right? So when it is doing the stretching, right? So where B is moved forward to some extent, A is moved forward to some extent here. So with equal distance, right? For example, here is 2 angstrom here distance, There is 2 angstrom. So equal distance is there. So it is symmetrical stretching. And in another case, for example, right? So here X is there, right? Here is a, here is a B here. And on pawn, energy absorption, B moved forward to a 2 angstrom here. A is, right, moved forward 1 angstrom. Or like 3 angstrom, right? So it is equal, unequal, sir, right? The unequal distances, the difference in the movement. So it is unsymmetrical stretching. And this stretching vibrations and bending nothing but where the and stretching here it leads to, right? Stretching leads to change in the bond length here, right? Is A and B, right? So it brings the changes in the bond length here. And bending, where, for example, the two atoms A and B here, right? So it is the delta, right? Bond angle theta. Okay. So upon vibration here, right? It may be come right side. It may be it is coming right side, or it is left side. It is left side, or it is right side and it is left side. Some. Okay. So on the movement of the atoms on the different directions here, right? So based on this, we have the different types here. Okay, so symmetrical and unsymmetrical. In that, we have rocking, scissoring, wagging, and twisting here. Right. So in plane bending, right? So in plane bending vibrations are two types here, like scissoring and rocking. Right. Here is one A. And here is it is scissoring. Scissoring is where this is coming, right? It is moving on left side and this hydrogen moving on right side here. So it looked like a scissors here, right? And with 1B, it is rocking, right? So the direction of the movement of the groups on the same direction, same side here, either on left side or the right side, right? And this is in plane. Okay, the in plane bending vibrations. And out of plane bending vibrations are two types again, wagging and twisting. Right. So here is a 2A. It is wagging. Wagging means where both are, right. Means out of plane here. Right. Here is a in plane rotation. When right here the in plane rotation like scissoring and rocking, and wagging and twisting is the out of plane vibrations here. Right. In the twisting, you know that here this particular hydrogen, right? So it is moving on plane here and it is out of plane. So like that, it is on, they move on the opposite direction. So we call it is a out of plane vibrations. Here the IR spectra plot is drawn in between the, right? Here is a IR spectra where it is drawn like this here. So you will have the, right? So it is drawn in between the transmittance. Okay. Uh, Here is plot is drawn between the light transmitted and the intensity here, right? That is the electron potential and the intensity. So here the frequencies of stretching vibrations increase with increase in the bond states here. Here the force constant of the bonds increase from the single bond to triple bond. For example, here C triple bond N, right, where it is stretching frequencies more than the C double bond N than C single bond N. So with increase of the number of bonds, right, the stretching frequency is increasing. So according the absorption frequency of those bond are about 2250 centimeters and 1650 and 1250. For example, for the C triple bond N, here C triple bond N stretching frequency is 2250 centimeter inverse, and C double bond N it is 1650 here, and C single bond is it is 1250. So with increase of the number of bonds, the stretching frequencies increases, and with increase of the mass also, the atom mass also, the frequencies are going to be increases. Okay, so here, so with increase of the atomic masses, the stretching frequency will be decreases. Means it is inversely proportional. For example, CBr bond. Bromine is a heavier atom, so its stretching frequency is 500 to 600. And CCl, where the chlorine is a less atomic weight when you compare with the bromine, right? Where the bromine is right, so bromine is it is 35, and chlorine is it is 17. It is bromine is 79, or when it is in the atomic isotopic form, it is 81, 79 and 81. Bromine, right? Here the 71 and 81, the isotopic form. And chlorine it is 35 and 37, right? So mass of the bromine is higher, so where its frequencies, stretching frequencies 500 to 600 centimeter inverse, and chlorine is 1600 to 1800 here, and fluorine which is increased to the 1400, right? So OH is 3570. Means OH is very less atomic weight. Okay, so like that, with increase of the mass, the frequencies, absorption frequencies will be decreases. Here is some frequencies, absorption frequencies of various functional groups is given. For example, here OH stretching frequency, the OH bond is there. So stretching frequency, uh, when the OH hydrogen is in the free form, free hydroxyl alcohols and phenols, it is 3640 to 3610, right? Where sharp, okay, sharp peak is observed, and OH stretching frequency hydrogen bonded in the alcohols and the phenols is 3500 to 3200. That means when the OH group is in the hydrogen bonding, involved in the hydrogen bonding, where the stretching frequencies decreases, right? Free OH is having higher stretching frequency value here, 3640 to 3610, and OH is in the free form, its stretching frequency is 3500 to 3200. And NH amines, NH stretching frequency, primary amine, secondary amine, and amides. It is 3400 to 3250 here. And OH stretching frequency when it is in the carboxylic acid, it is 3200 to 2500, 3300 to 2500 here, the carboxylic acid. And the C triple bond C, uh, right, CH stretching frequencies in the alkynes here, 3300, 32, 32 feet 70 here. And the CH stretching frequency in the aromatic double bond or the single bond. The single bond CH stretching frequency 3100 to 3000, and CH double bond, right? Double bond CH stretching frequency in the alkenes, olefins here. Its stretching frequency is 3100 to 3000. And aldehydes, okay, the aldehydes is 28 to 32. Aldehyde CH stretching, okay, aldehyde CH stretching is it is 2800 to 26 955 here. And the C triple bond N stretching is 22 60 to 21 20 to 10 in the cyanides, nitrites. And alkynes C triple bond C stretching is 22 60 to 21. And C double bond O stretching frequency, the carbonyls like aldehydes and ketones is 1760 to 1665. And C double bond O stretching frequency in the carboxylic acid, it is 1760 to 1690. The CH stretching frequency in the carboxylic acid, the OH stretching is 3300 to 2500 here, right? And the C double bond O stretching frequency in the carboxylic acid is 1760. And in the esters and saturated all aliphatic compounds, the C double bond O stretching frequency is 1750 to 1735 here. And in the aldehydes, it is 1740. Okay, and primary amines, the NH stretching bending is 1650 to 1580 here. So this is the list of the absorption frequencies in the IR spectra, where the particular functional group is appeared in the IR spectra. This is the group frequencies like CO stretching frequency in the alcohols, in the alcohols, okay, carboxylic acids, esters, and ethers. It is 1320. It is a characteristic, right? It is a characteristic signal to differentiate the carboxylic acid, esters, and the alcohols. 1320 to 1000. CN stretching frequency, it is 1250 to 1020 aliphatic amines. And double bond CH stretching frequency, the alkenes, it is 1000 to 650. So here the characteristic IR absorption frequencies of functional groups. So the individual functional groups absorption frequency and given. So we'll see how the IR spectra is appears and what are the characteristic frequencies. So here the carbonyl compounds. A peak due to absorption by carbonyl group is expected in these compounds. The frequency of stretching vibrations varies with the nature of the carbonyl compound. Aldehydes and ketones. The aliphatic carbonyl compounds, the frequency is 1720 to 1740 here. And the carbonyl compounds in the cyclohexanone, is 1715. And in the aromatic compounds, alpha beta unsaturated aliphatic carbonyl compounds is right here the aromatic carbonyl and alpha beta unsaturated. It is 1670 to 1690. The normal aliphatic carbonyl compound is 1720 to 1740 here, and aromatic and alpha beta unsaturated carbonyl compound 1692 yes 1670 to 1690, and aliphatic carbonyl compounds involved in the hydrogen bonding is 1600 to 1640. And saturated cyclic ketones, four-membered it is 1775, and five-membered ketones 1740 to 17. Six-member and higher it is 1705. Right. So the absorption bands the is given here. The CS aldehyde CS stretching frequency. Right. Here is a 2738 aldehyde, and CO stretching is here is a 1720 something. Yeah, the butyraldehyde spectra is given where CO stretching is appears at 1700 or 1710 in range of that. Okay, 1690 to 1700, and 1363 is there. And esters. So saturated cyclic esters, it is 1735 to 1750 centimeter inverse. And saturated cyclic esters, five member when it is P lactones here, it is 1820. And with increase of the cycle, like six member, where it is decreasing 1760 to 1780 here, and seven members lactones where it is 1735 to 1750, and for larger rings also this frequencies observed. This is the I aspect of methyl acetate. Right? So in the methyl acetate, the CO stretching frequency observed in the range of 1725 something, and CO stretching frequency observed at 1048. Alcohols and phenols. The monomolecular unassociated alcohols 3590 to 3650, and intermolecularly hydrogen bonded OH group is 3450 to 3550. So here is the example is given for a secondary butyl alcohol. So OH stretching frequency, it is appears in the range of where it is appearing generally it is 3400 somewhere here, right? So 3400, and CO stretching frequency is observed in the range of 1050 to 1100 somewhere. And the phenols. The phenols, here the monomolecular phenols 3650, and the hydrogen bonded phenols at 610. The hydrogen bonding is decreasing the absorption frequencies here, right? And the intermolecularly associated phenols 3100 centimeter. Here the paracresol is given with the weight stretching frequency, the paracresol, where it is observed in the range of 30 is 3600, right? Here there are 3600 somewhere here, 3650 somewhere. And the CO stretching frequency is observed in between 1330, where it is 1235 somewhere, right? 1235. Carboxylic acids. Here, the stretching vibrations frequencies of carbonyl and hydroxyl groups in the carboxylic acid. So it is carbonyl is appears in the range of 1700 to 1725 here. The double bond group in the carboxylic acid. We have the carbonyl as well as the OH, right? So OH and carbonyl. So carbonyl appears here. The OH appears in the range of 35, 50. It's at 3520 somewhere. So two characteristic absorption frequencies in the carbonyl carboxylic acids here. And the OH stretching frequency, it is the broad, right? Because it is involving in the hydrogen bonding. So it will be observed in between 2500 to 3000. Right? So here the acids CO stretching frequency. Right. So we have the carboxylic acid, we have C double bond O, CO, here, right? So this is one band, this is another band here, and this is another. There are three characteristic peaks observed in the carboxylic. And here CO stretching observed in the range of 1250 centimeter inverse. The OH it observes in the range of 1400 to 920. Here some example is given. Carboxylic acid, propionic acid is given, right? So here the propionic acid, the OH stretching frequency is observed in the range of, where it is observed here, 3400 somewhere here, right? So 34, right? Here it is 32, some 3250. And the CO stretching is observed in the range of, where it is the 1213. So CO stretching is observed the range of 1250 here, and OH is observed the 950. to amine. So the NH stretching frequency in the primary amine, when it is in the free form, is appears in the range of 3400 to 3500. The secondary amines, the free form means without hydrogen bonding, it appears in the range of 3300 to 3500. And like your OH groups, that amines NH groups also having showing the broad uh, peak NH peak here because they involves in the hydrogen bonding. Okay, so here, so besides the CN stretching, it 10 here the 1030 to 1230 centimeter units. For aliphatic compounds, there are two at 1180 and 1360 strong for the aromatic compounds here. There is a IR spectrum of the isobutylamine. If you observe this, right? So where here is a NH stretching frequency. So it is appears in the range of 3400, and NH bending frequency it is appears in the range of where the 1400 somewhere, and CN nitrile stretching frequency appears in the range of 1050 or 1020. Okay, and amides. For the amides, amides also we can classify into three types like primary amide, secondary, and tertiary here. So primary amide, it appears in the range of the primary amide. So in the amide, we have the C double bond O and NH here. Okay. So the carbonyl stretching vibrations in the amide Cs. Right? So amide means here C double bond O, C double bond O, and NH. Okay. So we have CO, carbonyl, and CN. Right? So primary amide carbonyl appears at 1650. Secondary is 1630 to 1680 here. Tertiary 1630 to 1670. And the NH stretching frequency, here the NH, CN and NH also we have. So NH stretching frequency, two bands are observed at 3400 to 3500. And primary amide bonded two band. Here is a free. Here is a bonded with means hydrogen bonded. So 3100 to 3300. Secondary amides you can see at 3430 here. And secondary amine with hydrogen bonding 3140. And here's the amide CONH2 shows the absorption due to NH stretching in the range of 3050 to 3550 here. Means besides C double bond, right? NH and C double bond O. So it have the another characteristic CN stretching frequency. Okay, that is 3050. There is a benzamide, benzamide here. So in the benzamide, so you can see the carbonyl here, right? NH here, and aromatic C double bond C here, CH here. Okay, so these are the characteristic absorption bands here. So NH stretching frequency bending is observed at 1581, and the CO stretching frequency is observed at 1659, and NH stretching frequency observed at 3420 something. The CO is at 1659. And here this band is for CH stretching. And for nitro compounds, the nitro group, the aromatic compound, given two strong peaks at 1300 to 1370 and 1500 to 1570. In aliphatic nitro compounds, these peaks observed at 1370 to 1380 centimeter. Next, metal ions in the biological systems. So here the importance of the sodium, okay, the metal ions, sodium, Na plus, potassium, ferrous, ferric, and carbonate, and right, carbonates in the biological system. What are the role of these metal ions in the biological system? We'll see. Here the sodium, potassium, magnesium, and calcium. These ions, they have a great biological importance in the metabolic systems here, where the 99% of the total metal ion concentration, right, it will be constituted the biological system. And like zinc, copper, cobalt, these are the next abundant metals in the biological systems. So first we'll see the bio inorganic chemistry of ferrous, cobalt, and zinc. So here, hemoglobin. Here is the protein. Right? So in the protein, where the iron is present, hemoglobin protein, the iron is present 65% here. The number of atoms of iron in the molecule is 4, and oxidation states is Fe plus 2, and the function is oxygen transport. And myoglobin protein, where the iron is percentage is 6% here, and number of atoms, iron atoms is present is 1, and it is present in the ferrous here, Fe plus 2, and its function is storage of oxygen in the muscles. And transpep yeah, transperatin, it is 2%, less percentage is there, and the number of iron atoms is ferrous atom is 2. It is present a ferric Fe plus state, and the function is transport of iron. Next, cytokinin, very less percentage, 0.1 percentage here. And one iron Fe molecule is there, atom is there, and its oxidation state may be ferrous or ferric here, and terminal oxidation. It involves in a terminal oxidation. Here is a hemoglobin structure. You can see. So here you can see iron. The cytochrome. So this plays an important role in the transport of electrons in the photosynthesis here. These are three types A, B, and C. C is the most important. This receives electron from strong reducing agent used to the oxidizing agent. This contains iron in the plus 2 form and plus 3 oxidation states here. The molecular weight of cytochrome is 12,000 daltons here. And its function is it releases energy release in the process of oxidation